Hi everyone, in this particular video, we will start talking about the conformation analysis of butane. Butane is a 4-carbon alkane, so I've drawn it out here, okay? And I'm focusing on certain aspects of this molecule. Now realize that for butane, because you have so many carbon-carbon bonds, right? You have 1, 2, and 3 carbon-carbon bonds. You could do different conformation analysis. But in reality, also realize that you can only do 2 conformation analysis. You can do the conformation analysis about C1, C2, which would be the same as C3, C4, because it's the same arrangement, right? Or you could talk about a conformation analysis about C2, C3 bond, okay? Now, what happens if we did a conformation analysis about the C1, C2 bond or the C3, C4 bond? So I have a model for butane here, and let's just imagine that this here is my C1, okay, in red, C2, C3, and C4, okay? So if I look at the C1, C2 bond, okay, and we are looking at an eclipsed conformation here. If you look at the eclipsed conformation here, okay, what you would notice is that this is not that different from like propane, let's say. Okay, the only difference I see here is that the group here is now much bigger. So that means the energy of this eclipsed conformation would be higher compared to like propane. Now, as I rotate about this C1, C2 bond, we go to a staggered conformation, right? And then eclipsed, and then staggered, and then eclipsed. So we just keep doing that. But we should get a profile for the conformation analysis, which is very similar to what we saw in ethane or propane. The highest energy is going to be the eclipse conformation, comes down to the staggered, goes up again, okay? And then goes up and down in waves, essentially. Now, this was our C1, C2, and notice how the C3, C4 bond is pretty identical. There isn't like a huge difference here, okay? It's just a different carbon-carbon bond, but in terms of like the group, it is the same, okay? So there isn't like a huge difference there, okay? Now, but butane, now it gets interesting when we talk about the C2, C3 bond. So if we talk about the conformation analysis about the C2, C3 bond, so that is what we will focus on in this particular video. And in fact, I'm going to draw some of these conformations out, and then we'll come back to the model and then work it out, okay? So let's start by drawing the conformations of butane about the C2, C3 bond. Now, you can look about the C2, C3 from the left, or you look at it from the right, you will get basically a flipped over. So I'm looking at it from the left. Okay, C2 is my front carbon, C3 is the back carbon. So if I draw what I see right now, okay, whatever I'm seeing right now, if I draw that, when I look at C2 from the left, what I see is the CH3, which is carbon 1, pointing down in the plane of the whiteboard. Okay, so there is a CH3 group pointing down. There's a hydrogen on the wedge coming out. There's a hydrogen on the dash going in. So that means there is a hydrogen to my right, and there is a hydrogen to my left. Okay, that is the front carbon. We are done with C2. Now, C3 behind C2 is a circle. And on C3, I see a CH3 group, which is the carbon 4 with the hydrogens on it, okay, pointing up in the plane of the whiteboard. So straight up, I'm going to draw now the CH3, okay? And then I have hydrogen on a wedge, hydrogen on a dash, both pointing down. So to the right bottom and to the left bottom, okay? Or the upper, the bottom right, the bottom left, I'm going to draw the 2 hydrogens. So this is the conformation of butane that I've drawn on the board. And I think what I'm going to do is just to track these, I'm going to label these carbons. So this was C1 and that was C4, okay? Those are the 2 carbons. C2 and C3 are here because that's the bond that we're focusing on, okay? What would happen if we do a 60-degree rotation on this molecule. In fact, we're going to draw all possible conformations here. Quickly work through it. So we're going to do 60-degree, and then we are going clockwise. That means to the right. Okay, that is how the molecule is rotating. Now, whenever you're doing a conformation analysis, you're drawing different conformations, do not move both carbons simultaneously. Okay, clockwise. So I'm going to define what I'm moving. Okay, I am moving the front carbon. The back carbon is steady. That's constant. That's not moving. Okay, if I move both carbons simultaneously, then it's going to get too messy to keep track of. So I'm doing a 60-degree rotation clockwise on the front carbon. I've defined what I'm doing. The back carbon remains the same. Okay, so what I'm going to do is, since the back carbon is not moving, I'm going to draw the back carbon in, because that's not changing here. Okay, so I have the CH3 at the top, hydrogen, and then hydrogen here. That is the back carbon. Nothing changed about it. Okay, so this is still the C4. Okay. Now, the front carbon, which is this, rotates by 60 degrees. Okay, so 60-degree, notice, is this angle. That dihedral angle is 60 degrees. All of these angles, they are 60 degrees each. So if I rotate by 60 degrees, what that means is this hydrogen here, or let's say if we follow the methyl, probably easy, okay, this bond angle is 60 degrees. So if we rotate this by 60 degrees, what that means is this CH3 should come next to that hydrogen in an eclipsed conformation. So I'm going to draw the front carbon in, and I'm going to draw the CH3, and that C is carbon number 1. Similarly, this hydrogen goes next to that CH3, so I'm going to draw that hydrogen here, and the other hydrogen goes next to this hydrogen, so I'm going to draw that hydrogen here. So I have an eclipsed conformation, right? The next eclipsed conformation that's possible. Okay, we'll go again, okay? So I'm going to draw another conformation, again 60-degree clockwise on the front carbon. That is what I'm going to do. So I'll draw the back carbon again. We have the CH3, hydrogen, and hydrogen. That's C4. Now, 60-degree rotation. So this CH3 is going to come up here. Okay, from the front carbon, we have CH3 here. Hydrogen will go there, and the other hydrogen is going to come down here. Okay, so we have now C1 and C4. Again, another 60-degree conformation change. Okay, 60 degrees again. Got CH3, hydrogen, and hydrogen. So notice how the back carbon is not changing. It is constant compared to the first one. Okay, that does not change. And the front carbon, okay, this is C4. On the front carbon, we have CH3, have hydrogen, and we have hydrogen. Okay, and so this carbon here is C1. So we have C1 and C4 over there. Okay, and now I can do another conformation here, 60 degrees. So back carbon, again, there's no change. Hydrogen, hydrogen. On the front carbon, I've got CH3 here, hydrogen, hydrogen. This is 4, this is 1. another 60 degrees. So these are all 60-degree rotations. And the reason why we're doing the 60-degree rotations is because the staggered and the eclipsed conformations are the easiest ones to keep track of. Remember, there are numerous conformations in between, but they're difficult to track. Okay, these are the ones that we have a name for, and we know about their relative stabilities. Okay, the relative stabilities are easy to track here. That is why we're doing the staggered and the eclipse conformations by moving 60 degrees. So we've got CH3, hydrogen, hydrogen. Okay, and so from this carbon here, we've got CH3, we've got hydrogen, and we've got hydrogen here. We've got C4 over there, and C1 is here. Those are the conformations, and then we can do one final conformation. In fact, I'm not going to draw this in, but if we did another 60 degree, we will come back, right, to the first conformation here, because now this method will come down actually. So we would have done like a 360 degrees right now, okay, at this point. Okay, so now that we have all the conformations here, we're going to evaluate their relative stabilities. Qualitatively, we're going to talk about, okay, which one of these conformations should be like the most stable, which are similar, which are not, things like that. Okay, so let's start there. Okay, first, let's try to identify some conformations that are similar, like, or maybe like identical. You think that, you know, the nature of the repulsions there, you know, would be the same. Maybe they are both eclipsed, or they're both staggered, and they have the same group staggering or eclipsing, which means their energies should be the same. So let's see if there are any structures like that. And in fact, to help with the process, let me just go ahead and label some of these, label these structures. Okay, so let's say we have 1, 2, 3, 4, 5, and then 6. Okay, so those are the structures that we have. So let's see if there are any conformations here that are identical to each other, or at least looks like they are just a flipped version or something. So if you carefully look through these, okay, and as I'm looking through these, I think structure 4 and structure 5, okay, sorry, I did not label these correctly. Okay, this is 3, and this is 4, 5, and 6. Okay, so as I look through these, what I notice is that structure 3 is the same as structure 5. They're just flipped over. Okay, this is equal to structure 5. Okay, they're the same in terms of interactions. Notice how they're both staggered, and they have the two methyl groups with a 60-degree dihedral angle between them. The two methyl groups are a 60-degree dihedral angle. Everything else is same over them. So that means they must have the same energy. Are there other conformations which are the same? It looks like structure 2 should be the same as structure 6. Okay, this should be the same as structure 6. They should have identical energies, because what I see in structure 2 is that it's an eclipsed conformation. Structure 6 is also an eclipsed conformation. In structure 2, there are 2 hydrogens eclipsing each other. Structure 6 has something similar. And then there is 1 methyl and hydrogen eclipsing, or 2 methyl hydrogens eclipsing each other. And in structure 6, we have 2 methyl hydrogens eclipsing each other. That means they have the same sort of an interaction between the groups. So they should also have the same energy. Okay, so these are the same, but they're eclipsed. Okay, now we are left with structure 4 and structure 1. Those are the two that we are left with. And if we look at all of these, which one of these conformations looks like the worst, like in terms of it should be the least stable of all of these? I'm going to say that it must be structure 4, because in structure 4, the two methyl groups, the big groups, they're next to each other. Okay, this is eclipsed, and the two big groups are also next to each other. Okay, so this must be the least stable of all these conformations. Okay, like it must have the highest energy. Structure 1 and whatever we would have gotten here once we come back. Okay, this conformation has the two methyl groups across from each other. Their dihedral angle here, okay, the theta here is 180 degrees. They're across from each other, like the farthest away from each other that they can be. And so for that reason, what that means is this here is the most stable conformation here. Okay, and some of these conformations have special names. When you have the two big groups, okay, the biggest groups possible, or the biggest groups on each carbon, okay, we're talking about the biggest groups on each carbon. So if you look at the front carbon, it has two hydrogens and a methyl group. The back carbon has a methyl group and two hydrogens. So the big group on the front carbon is the CH3, the big group on the back carbon is the CH3. They are the farthest away from each other. That conformation is called an anti-conformation, and it is the most stable of conformations. Now, this can be expanded, applied to other molecules also. Anti-conformation is the most stable. Now, structures 3 and 4, if you look at those, okay, and okay, so we have the least stable conformation here, which is eclipsed. And again, this is the least stable because the biggest groups on the front carbon and the back carbon are eclipsing each other. So that's why this is the least stable conformation. When you look at structures 3 and 4, notice how there is a dihedral angle of 60 degrees between the two big groups, okay? There is a dihedral angle of 60 degrees between the two biggest groups on the front carbon and the back carbon. So these conformations, they have a special name. These are called Gauche conformations, okay? These are called Gauche conformations. And this interaction is called a Gauche interaction. Now, in principle, you could say that these two hydrogens are also Gauche to each other, okay? But then what does that mean? Does it mean anything? Like in ethane, if we talked about Gauche interactions, you might want to revisit, look at all those structures. We can talk about Gauche interactions there, but does that mean anything? No, okay? So the Gauche interaction or the Gauche conformation relates to this relates to this interaction between the biggest groups, because that's when the repulsion is going to be the biggest, okay? And so we have those, okay? So now let's look at these in a model. So essentially what we're saying is when we have butane, the first conformation, anti, is where the two methyl groups are across from each other. That means we're looking at something like this. This is the anti-conformation of butane. This is one methyl group, that's another methyl group, okay? They are across from each other. The molecule itself is staggered. There's like a 60-degree dihedral angle between all the groups, okay? This is a staggered conformation. And so then when we start moving clockwise, we moved clockwise, okay, 60 degrees, this methyl group comes here. So that's our structure 2. So this is an eclipse conformation, and notice how there is a hydrogen and a methyl eclipsing, and there's another hydrogen and methyl eclipsing here, and then there are two hydrogens eclipsing here, okay? That's an eclipse conformation where hydrogens are eclipsing with methyl groups. Then we went to the next conformation, which is a Gauche conformation now. Okay, this is a Gauche. Okay, so you notice how the two methyl groups in space, they're like really close to each other. Okay, now one thing you also want to remember is that what I'm holding here in my hands, okay, these are carbon-carbon single bonds. That means while the molecule is rotating about the C2-C3 bond, we are considering that rotation. The molecule is also rotating about these bonds. These are also rotating simultaneously. It's not like when the molecule rotates about one bond, the other ones are not rotating, okay? This conformation would mean that all of these are rotating simultaneously, okay? So that's the Gauche conformation. So the Gauche conformation is when you have this dihedral angle of 60 degrees between the two big groups. That's a Gauche conformation. Okay, now this is a staggered, but the Gauche interaction between these two groups is going to make it a higher energy. Okay, and then we have the worst of all the conformation. Okay, the highest energy is the eclipsed, where these two are basically in front of each other. And like I said, at this point, these groups are also rotating. And then you can hear something, right? When these are rotating, the groups, the bonds, they will bump into each other occasionally, okay? So that means there isn't enough room for these to like basically rotate at the same time in this conformation. That's sort of an interaction where groups interact in space. That's called a steric interaction, okay? Which basically means like a lack of space. So steric interaction. Okay, so that means this eclipsed conformation where the two big groups are next to each other, that also has a steric interaction. Okay, so this is possible in 4. And that makes 4 a really high energy conformation. And then beyond that, okay, once we're at this eclipse, we go to another gauche, as you see on the board. From here, we go to another gauche, and then to an eclipse, and then finally to the anti-conformation, which should be the most stable of all these conformations. Okay, now, when you're at a staggered conformation, the molecule is happy, but that doesn't mean that the molecule does not rotate, okay? It does rotate. Now, as the groups get bulkier, the molecule would have a hesitation to rotate. It's not going to rotate as much, okay? But for something like this, the molecule still rotates, okay? And so as it is rotating, it is going from a stable conformation to an eclipse conformation, which is less stable. So the molecule would have a tendency, or it would have a hesitation to rotate. It has to overcome an energy barrier here, because this is low energy, and as it goes to the eclipse conformation, you're going to something that's high energy. So it has to overcome an energy barrier, and that causes a strain in the molecule, and that strain is called torsional strain. Okay, torsional strain. Torsional strain. And the energy that's required to overcome this strain is called the torsional energy, okay? Those things, again, read in the textbook. So you can find these things in the textbook. But, that is the conformation analysis of butane. And what that means is I'm going to actually erase some of this and just replicate, just draw it simply here, okay? For butane, again, when you plot energy against dihedral angle, and we started with the anti-conformation here, so I'm going to start with 180 here, okay, and then we did a 60-degree rotation, so we're going to like 240, and then we'll go to 300. Either ways, whichever way you look at it, or you could go down from 180, you could go to like a 120 and then a 60 and then a 0. Either ways is fine, whichever way you think about it. Maybe since we are going to this conformation here where the dihedral angle is 0, we'll actually like go down here. So let's say 120, and then we went to 60, because this dihedral angle that we're measuring here is the dihedral angle between the two groups. So notice how the dihedral angle is decreasing here, okay? So it went from like 180 to like 120, and then to 60, and then to a 0, okay? So you went 60 and then 0, and then it will go up again 60, 120, and then we'll have 180. So what happens in butane is, as you go through these conformations, unlike propane or ethane or the C1, C3 bond of butane, where it basically goes up hills and valleys, and the hills are all the same height. That means you have the same amount of torsional strain or torsional energy. Unlike that, in case of butane, as we go up this, 180 degree is something stable. That's the anti-conformation. So we are now starting low. So you go up, you come down, okay? So notice how 120, 60 degree change is an eclipse conformation. When you go to a 60 degree, gauche is stable, but again, sorry. So the gauche is not as stable as the anti because there is a gauche interaction. So the gauche is going to be something higher in energy, over here when we mark it. Okay, so the gauche is like slightly higher in energy because it's not as stable as anti. Now there is a 60 degree dihedral angle between the two methyl groups. So the gauche is slightly higher in energy, and then we go to 0, that is the least stable. So it actually goes more steep. Okay, so that's higher in energy. And then we come down to another gauche. So it actually comes down to another gauche at this 60 degrees. Okay, and then it will go up to the same as that, and then come down to the other 180. Okay, and that 180 is going to be here. So you notice how the hills and the valleys, they are not the same depth or the same height, similar to like an ethane or a propane. So that is the conformation analysis of a butane molecule about the C2, C3 bond and how it gets complicated. But like I said, this can be expanded to other molecules, to any carbon-carbon bond. So if you're attempting to draw the most stable conformation, looking at a carbon-carbon bond for another molecule, what you're trying to draw is the anti-conformation. And if you're trying to draw the least stable conformation, then you're trying to draw this eclipse where the two biggest groups are at a dihedral angle of 0 degrees. And then you can always draw a gauche where the two big groups have a dihedral angle of 60 degrees. Okay, so let's look at an example of that. How would we draw some conformations for some molecules? If I had to draw it for like a hypothetical molecule, draw like the most stable and the least stable conformation. And I'm just going to come up with a molecule here randomly. Okay, so let's say we have a molecule like that, and we have a methyl group here, hydrogen here, and we have a methyl, and then we have a hydrogen there. Okay, and we have to, let's say, look at or draw the most stable and the least stable conformation about this bond. So when you see that arrow or maybe a numbering is given and it's like, okay, draw it about this bond, something like that. I think the numbering would be here 1, 2, 3, 4, 5, 6, 7. This is not a random numbering. I've actually numbered it according to an IUPAC name. Okay, so what I'm doing here is we're drawing it about the C3, C4 bond. We're drawing it about the C3, C4 bond. Okay. Okay, so C3, C4 bond, or this bond that I've shown now, C3C4. If I have to draw, we're going to draw the most stable conformation and the least stable conformation. If need be, we can draw a Gauche conformation also, okay, about that bond. How would I go about doing this? The first thing that I'm going to do is, before I think about what would be the most stable conformation or the least stable conformation, I'm going to just draw a conformation, a Newman projection, okay, of what I'm seeing right now. That is what I'm going to draw first, whatever I'm seeing right now. So it's drawn here, so I'm going to say that that C3 is my front carbon. And on C3, when I look at it from here, I see a 2-carbon group going up, okay, 2 carbons. So I draw 1, 2. So that's the 2-carbon group pointing up, or an ethyl group. If you're familiar with nomenclature right now, that's an ethyl group pointing up. Okay. There is a wedge and there is a methyl group over there. So that means there's a methyl group here. Okay. The dash is what's going behind the plane. So there is a hydrogen over here. Now notice this is a CH3 group. I do not have to write anything over there. And this would be read as a CH2, CH3, and an ethyl group. That's what I have here, CH2, CH3. Okay, you're done with the front carbon. Let's go to the back carbon. On the back carbon, pointing down is a methyl group. So pointing down is a methyl group. On the wedge, I have 1, 2, 3 carbons. So a propyl group on the wedge to my right. So to the right, I'm going to draw 1, 2, 3. Okay, this is the back carbon. So coming off the back carbon are 1, 2, and 3. So that's basically 5, 6, and 7. This is 2, and that's 1. Okay, this was 3, and this here is 4. That circle is 4. Okay, in terms of carbon numbering here. And then on the left or on the back, I have another hydrogen. Okay, so what I've done here is basically drawn what I'm seeing here, the exact molecule, the Newman projection for what I'm seeing in 3 dimensions. Now, once I've done this, I have to draw the most stable conformation, which means I have to draw the anti-conformation, and then I have to draw the least stable conformation. The most stable conformation is going to be the one where the biggest group on the front carbon and the biggest group on the back carbon are at a dihedral angle of 180 degrees from each other, or they're across from each other, anti to each other. So let's identify the biggest group. So on the front carbon, I have a hydrogen, there's a methyl, and there is an ethyl group, a 2-carbon chain. So that is the biggest group on the front carbon. Okay. On the back carbon, I have a hydrogen, I have a methyl, and then this 3-carbon chain. So that must be the biggest group on the back carbon. So now that I've identified these, I have to draw an anti-conformation. That means they must be across from each other. So what that means is this group needs to come here. Okay, in my head, when I think about it, that group needs to move here. And now you just cannot like replace things. It has to be a rotation. So if that group comes here, what that means is this methyl group has to go here, and the hydrogen must take the place of that big group. Okay, I'm imagining a rotation in some direction. You could rotate in either direction. That doesn't matter. Okay, it's not defined that you have to go clockwise. You can go counterclockwise. But I'm going to draw what I have here right now. So I'm going to draw the front carbon again, ethyl group up from there. Okay, methyl to the right, and then hydrogen to the left. And then on the back carbon, which is a circle, the propyl group is at the bottom. Okay, so I have 1, 2, 3, propyl group at the bottom. then the methyl group went up here. Sorry, the methyl group is up here, and the hydrogen went on the other side. Okay, so that would be the most stable conformation. Now, if I just put this biggest group here, but if my methyl group and hydrogens are swapped, okay, would that still be the same molecule? Okay, let's see, how would that happen? Could that happen? When this comes here, can this hydrogen stay in the same place? The answer is no. Then we are looking at a different molecule in terms of orientation, okay? So it is very important that you keep track of your groups, and they must rotate, okay? Like all the groups on a carbon must rotate. So I have the anti-conformation. Now the least stable conformation is going to be when the two big groups are next to each other. So again, if I do a rotation on the back carbon here, okay, the front carbon is already drawn out, and on the back carbon, and I can start from here, that is where I started. So the least stable would be when the two biggest groups are right next to each other. So I'm going to move this counterclockwise by 60 degrees just to put it next to that. So I'm going to say there is 1, 2, and 3 groups, or 3 carbons over there. Okay, they're eclipsed. So if this moves counterclockwise by 60 degrees, that means this methyl should move counterclockwise by 60 degrees. Okay, so that methyl is over there. And then the hydrogen must move counterclockwise by 60 degrees. So that hydrogen is also here. So that is the least stable conformation, where the two big groups are right next to each other. And for this particular conformation, notice how the two methyl groups also got next to each other. They're not the biggest groups, but that's also like less stable because they're big groups, big enough, not as big, but like they're slightly bigger groups compared to hydrogen. So they're also there. Okay, so that would be the least stable conformation. Now, do we need to draw a Gauche conformation here? If you look at this first conformation that I've drawn, right, the dihedral angle between these two groups is 60 degrees. That means this here is actually a Gauche conformation. So we have all 3 conformations on the board. Now, in some cases, it is possible that when you draw out your molecule, you might actually get to the anti or the least stable conformation, and then you just have to work to the other conformations that are possible, okay? But these are the important conformations that we will be, that we sort of care about at this point, or the ones that would be most interested in. So I hope that helps, okay? But you can do conformations, and you can rotate about carbon-carbon bonds, and you can come up with different orientations which are different, which are of varying stabilities now, okay? Some are more stable than others, okay? This is the most stable conformation. This is less stable. That is the least stable conformation, okay? Bye.